My name is薛宏中from the Danjiang Daxue. First of all, I would like to thank the nice invitation from the organizer. And this is my talk. The title of my talk is Optical Properties and Excitonic Effects in Atomic Layers of Hexagonal Boron Nitride. And this morning, Steve, he provided a very nice talk, highlights how important of the environmental screening on the effects on the excitonic effects of the low-dimensional systems. So my talk just following the same idea, and try to give you some example, especially for the boron nitride related materials. This is my outline. I will just give you some discussion of the excitons in solids, and I also want to summarize the recently theoretical and also the experimental works on the how to just study the excitons in either conventional semiconductors or low-dimensional nanosystems. And I also will give you some a little bit insight of the method we use to try to calculate or to understanding the exciton effects in the systems. And I will just give you the some examples for the recent progress on the theoretical study of the low-dimensional nanosystem from things like one-dimensional nanotubes, and then go to the two-dimensional, and then finally I would like to just show you how about the dimensionality effects on the exciton property of the, especially of the boron nitride systems. And finally, I will give you conclusions. Right. Before I move on to my talk, I would just would like to emphasize why recently so many researchers or the groups, they was just like focus on the boron nitride systems. That's some reasons, because the boron nitride, they have the wide band gap, and also a very good chemical thermal stabilities, and also they have a very high mechanical strength. That means it could be work even in very extreme conditions. And also for the optical considerations, they have the strong exciton emissions in the far UV regime, and finally that's quite good the candidate to form the functional multi-layer heterostructure, especially with the graphene, because they have the highly similarity about of the structures, especially like the lattice constants and also interlayer separations. And recently, actually the low-dimensional boron nitride system has been successfully synthesized. For example, just you can use in the CVD methods. You can just go to see this is the Rice University groups, Jiayan's groups, and they can just successfully synthesize the few layers of the boron nitride, large areas, and with quite good quality. And also, you can just make this kind of low-dimensional system through the explorations, and that's been done by the Andrew Ginn and their groups, and they're using just explorations, mechanical explorations, and from the high quality of the hexagonal boron nitride bulk. Here I just summarize a bit how we to probe excitation properties in solids. Well, from the spectroscopy, normally people using the optical absorption, emissions, or reflectivity measurements, and I will just basically relate to the optical property. And also the another quite people use to detect the exciton, or to measure the exciton effect using the EOS, the electron energy loss spectroscopies. And recently, and thanks to the modern progress on the elastic X-ray scattering, these few groups now, they could just perform this kind of measurement, try to study the exciton and also study the dynamic behavior of the exciton, things like the dispersion of the exciton. And on the other hand, theoretical approach and people, you can use in things like the model, and using a simple model like the envelope function approximations, and try to solve this kind of Schrödinger-like equations. And you can just, the key idea is just how to get a proper dielectric functions or dielectric constant in this formula. And also another type of model they can use in a two-label model, something like that, and you can just try to solve the model. And but both of them is you probably need the input from the experiments or things like the empirical type. And on the other hand, the other approach, and you can use in either this time-dependent density functional theory, or either just what we use in here, just GW, and plus the beta solving that we call the Ab-initio quasi-particle calculations. And before we're talking about the results, let me just show you the famous diagrams try to highlight how bad of the static density functional theory, and especially for predicting the band gap resistance. This kind of underestimate not only happening in the conventional semiconductor systems, but also you can find this kind of the overestimations in the molecular systems and also for the surfaces. So that should be, we have to do some kind of corrections for this kind of electronic structures properties before we move on to discussion to discuss the optical property of the systems. And the idea, the key issue of the many-body perturbation theory is related to just the fundamental theories of the GW methods. That's just because we want to just accurately describe the electron-electron screenings, and that will give us quasi-particular pictures. And that will be the most important idea, make the GW quite different from the other method, including the time-dependent density function theory. And the idea is simply just how can we just get how can we understand the accurate screening properties of the electrons in the solids. So if we can just calculate, done the GW properly, and we can just connect our calculations results with the directly with the experimental setup. For example, you can just we can just compare our calculated quasi-particle energy directly with photo emission and indirect photo emission and photo emission as well. And this is kind of more detailed, but I won't just just go to the very each equation line by line. I just want to highlight when we try to perform something like the many-body perturbation theories, and we definitely need to do some kind of more complicated, or you can say the more process of the calculations. We have to deal with the self-energy collectively, and also the key the key information, just the dielectric property of the systems. So in here, we using the GW approximation that will just for our calculation, we just give the high orders, for example, the vertex effects in the calculations. And once we obtain the quasi-particle energies, and we can just perform the further to take into account the electron-hole interactions by solving the Bethe-Salpeter equations. And that is Bethe-Salpeter equations. The formula is basically similar like the Schrödinger type equations. But the most important part of this equation is the kernel try to describe the interaction between the electron and the hole. And finally, we can just, based on the solution of these Bethe-Salpeter equations, we can just form the exciton wave function by simply just a convolution of your the quasi-particle, quasi-electron wave function and quasi-hole wave functions. Since we want to apply this kind of scheme to the low-dimensional systems, and also for lots of the density functional theory or first principle method, they're based on using this periodic boundary conditions. So, so we have to to include some kind of a truncation of the inter-unit Coulomb interaction, because the Coulomb interaction itself is long range. So if you're not doing these kind of truncations, and then in your calculation you will include some kind of fictitious Coulomb interaction between the body you want to calculate and also it's the image in the next supercells. So there are a few types of the truncations. It really depends on what kind of geometry of your low-dimensional systems. And you can see there's one example done by Dickerson's groups. They show how fast it converge if you just include the truncations, and you can see the band gap of the hexagonal boron nitride one layers. It can just converge very quick. Even you include the back. In your calculation you only just use the vacuum spacing about just only 10 Armstrong. But I should emphasize this is only the case for the hexagonal boron nitride. But if you deal with other kind of the low dimensional system, you have to check the convergences of your vacuum spacing, even you including truncations. So that is the flow chart of the calculation we done. Basically, my calculation is using the Berkeley GW just developed by the Stevens group. And so for performing the calculations, we have to solve the Coulomb equation first, and you get the ground state properties, and you then move on to the GW methods, and just try to solve this kind of Dyson equations, and you can get the self energy and also the quasi-particle and the energy, and then you can, once you get these energies, and then you can just solve the exciton property by solving the Bethe-Salpeter equations. Okay, so let me just show you, once you include the GW, then you can just dramatically correct your band gap of many systems, like here. Although they still have some systems not perfectly being healed by the GW methods, but again, because our calculations is starting from the mean field, ground state properties, and also the perturbation method. So the starting point sometimes it is will just affect your final result. So especially for some transition metal oxides, like the zinc oxides, or the other just have the transition metals, and that will, dealing with this kind of system, you might think carefully about your starting point. In this table, I want to show you the GW corrections for normal or conventional semiconductor, or things like box semiconductors, and you can see that was just the correction is about for the band gap is about 1 eV, but for low dimensional systems inside the tubes or sheet, that can be up to 2 or 3 eV. That means GW. That means the screening effect is more important in low dimensional systems, like this is a 1-dimensional or 2-dimensional. And recently they have another PRL paper. They try to using the GW plus beta subfield methods and try to understand the variation of the exciton binding energy in some typical box semiconductors, but they're using, because this kind of semiconductor is normally is a linear type excitons. So he just studied using the linear model and try to find out the scaling law of the binding energy as a function of the exciton radius. Okay, and so this is a kind of just highlight the beta subfield equation plus GW really can just provide a robust result, and also can explain why the zinc oxides have the strong, larger binding energy than the gallium arsenide. For the hexagonal ball nitride box systems, and they also they have a very strong exciton effect. Otherwise, and on the other hand, they also have the very anisotropic property of the excitons. And in this work, they present the non-resonance in electric X-ray scattering results for the hexagonal ball nitride box systems along the different Q directions. And you can see the shift of the exciton peaks is quite different along the different systems, and they recognize this kind of behavior just regarding to the different exciton properties. So that is their RPA's results. Now, let me just move to the one-dimensional. What is more important effects of the screening in low-dimensional systems? First of all, because in lower dimensional systems we have the you have the lower the periodicity directions. So, for example, you for the one-dimensional nanotubes only can have the one directions of the periodic conditions. For two-dimensional system, you have two directions of the periodic conditions. So you will lose some kind of periodicities in your systems compared to the three-dimensional box systems. So at that kind of case, you will have the dielectric confinements, and this confinement will just give the more chance for the electron and hole interaction can strengthen the interaction between electron and hole. So that is kind of one of the reasons why the low-dimensional system have a stronger exciton effect. Another interesting behavior that's been found by Steves, and they show there is one very interesting unique screening behavior. It's called the anti-screening behavior in carbon nanotubes. Actually, it is similar as the Steve. This model he demonstrated the dielectric function as a function of the radius or of the Q. You will find the low-dimensional system, especially the one or two-dimensional systems, and your dielectric function is non-homogeneous like the three-dimensional system. So that kind of the dielectric functions properties will just enhance the electron-hole interaction in these kind of systems. And for this two-dimensional systems, people also think about that be possible using the hydrogen model, try to fit their results and try to just modify to understand the exciton properties of this kind of resistance. For example, this work done by the PRL's papers. They study the dielectric function of the tungsten disulfides. They show the deviation of the two-dimensional systems away from the hydrogen model. And in one-dimensional systems, we also need to consider not only the vacuum's effect, because when you roll your layers to form the tubes, that could be enhance the orbital rehabilitations. So that kind of electronic rehabilitations can also affect the dielectric function, and also finally just will change the optical or electronic band gap. Just skip that one. And this this kind of huge excitonic effect is also also found in the boron nitride nanotubes. And you can see that for the boron nitride nanotubes, they have large band gap, and you have fuse some of the dark exciton as well. And you have people also found that the excitons can be composed by the several subband pairs transitions. So this is one-dimensional systems, and then finally I also want to show you if you have different materials and you're gonna see your exciton wave function have different localizations. That really depends on your materials. Now, for the two-dimensional systems, and this morning Steve just showed the MOS2 and also his work on the natures, and to show the tungsten disulfides. They have the very unique optical properties. And for the two-dimensional system, as I say, because the boron nitride is very similar as structurally is very similar to the graphene. So people think about not only just try to synthesize or try to just theoretically consider the possibility of this kind of in-plane heterostructures of the boron nitride and the graphene. And they also found this kind of system has very strong acetone effects, depends on your doping concentrations. And we also found that this kind of behavior can be exist in the cluster type of the doping of the boron nitride in the graphene. And now, for this kind of one-layer structures, and there's one work, they try to find the scaling law of the X binding energy and the quasi-particle band gap. They found some kind of linear behavior for the different type of the two-dimensional systems. So that it just they want to demonstrate the dielectric property could be similar to environments of these two different kind of two-dimensional system should be similar. But here is one data this morning I noticed the data is quite slightly different from Steve's result for the phosphorine. Because they show the binding energy is about 0.7 or something. I remember your result is about 0.5, so I don't know. Maybe the convergence have the problem, but yeah, let me just maybe discuss this later. Okay, for the few layer boron nitride sheet, as I say, you can use explorations, and people using the Raman to compare the intensity of the Raman to determine the number of layers. And you can just, for this kind of the measurement, you also can done the density function theory calculations to just compare the experimental result. On the other hand, you can using the optical the processes of optical approach to study the layers structures. For example, you can use in the luminescence, and you can shine on this kind of boron nitride flakes samples, and that's they demonstrate how about the how could you to decompose your original spectrons into the different contribution. That different contribution mainly just attribute to the different layer staking, and you can this result is again the GW plus beta submeters method. Okay, so what we also interested about when you try to staking the boron nitride layer, single boron layer from 1 to 1 and 2 and 7 and 3 and they keep going, and we want to see how the staking, because when you include more layers, and then that means you also change your environments. So we want to see how this kind of staking will change the screening property of the few layers. So in here I show you the GW and the LDS results. You can see firstly the GW will just dramatically just increase, open the gap, and also they will manipulate or just tuning the different the quasi-particle energy at different K points. So you can see for the different layers systems, your CBN could be different. Okay, also go to the hexagonal boron nitride, and we're going to find the VBN will be shifted from the K point to the T1 point here. So here I just summarize the quasi-particle the quasi-particle band gap as a function of the number of layers. As you can see, for the LDA, you can see they were gradually approaching to the bulk systems. But for the GW methods, this is the bulk band gap. But here you can see that's not quite straightforward. That's because in the few layer system, your dielectric function or your dielectric environment is still quite different from the bulk. But for the mean field, because you're using the only in the very rough estimation, so you keep it since like the constant of the dielectric function. So that will just explain why you have no discrimination. You can see that is the difference between the LDA and the GW. And our result can also compare to the experimental result recently done by Rice group as well. So you can see this is the UV spectrum of the different layer we calculate, and compare to the experiments. We can see the comparison is good. So that means we can just catch the quite accurately catch the dielectric environments of the low layers, few layer systems. And also we found, if we just look at the exciton wave functions, you can see when you're increasing more and more layers coming, and you're going to see the exciton wave function will spread out from the single layer to the next neighboring layer, because your environment, you have some kind of you have neighbors can let the electron move in. Okay, so this one I want to show you for when we just calculate the dielectric function. The optical band gap and also binding energy of the systems for different layers of the boron nitride, and we found this very interesting. For the optical band gap, we found is one region from, for example, from layer 2 layers to 6 layers. We found the optical band gap more or less it just stay the same values, and that's also found in the experiments. So we realized, because the reason why the optical band gap here is not just the continuous decrease as a function of the number of layers, because when you increase the layers and your environments can be changed, and that kind of change, the dielectric function change also affects electron screening and also electron-hole interaction. So these two interactions finally in this kind of few layer boron nitride system it cancel out. So similar behavior also found in graphene systems when they study the resonance peaks. They also found this kind of cancellation effects. And the last one I want to show you, if we just study the exciton wave function of the monolayers boron nitride, we also found the result in the tungsten disulfide. You have we found the sequence of the exciton orbitals since not like the hydrogen model. Now, okay, finally, this is my conclusions. I would like to just highlight first the dielectric confinement in few layers is quite important, and I will give you, contribute the binding energy larger than 1 eV, and also in few layer boron nitrides, it seems they have a cancellation of the electron interactions and electron-hole interactions, and that make the upper band gap almost more or less like a constant. And finally, the deviations of the hydrogen model also found in the quasi two-dimensional boron nitride systems. The last one, I would like to acknowledge my collaborators, Professor Louise and Professor Mei Zhou and Guangyu Guo and Wei Qingyi as well. Okay, thank you. Questions?
So from 3 monolayer onward, is the band gap similar to bulk already?
Actually, here is bulk. You mean the optical band gap?
Yeah.
Bulk is here. It's not quite similar.
So why is overshooting?
Because again, the first is the electronic behavior is slightly different because they modify the shape of the band structures, so you cannot see the.
So eventually you go up then?
Yeah. The fact you can see that in hexagonal boron nitride, your optical band gap may be measured from here to here, but for few layers it's from the gamma point, so it's slightly different. So that will also contribute the discrepancy between the bulk and
Oh, I see the nature.
It's not quite big actually. This scale is only 0.2 eV.
Okay, thank you.
Our next speaker is Professor Untitled. Let's welcome him.
Thank you for this chance to share our recent work with you. The title of my talk is